Let's start by reminding us what we did last time. Last time we were talking about BCS theory. BCS theory deals with the Hamiltonian This is Newtonian we start from. There's some interacting fermions, and of course everything is limited to the close vicinity of the Fermi surface. We then used mean field. To obtain the mean field Hamiltonian Ek alpha dagger k alpha k plus beta dagger k beta k. These are the Bogoliubov excitations plus E ground state, and we saw that Ek is equal to the square root of Vf k minus kf squared plus delta squared. We saw that this delta self-consistently is 2 omega d by e to the minus 1 over lambda, where lambda is n of 0 times v, and n of 0 is kf squared divided by 2 pi squared vf in 3 dimensions. We also saw that Tc is equal to 2 omega d by e to the gamma over pi e to the minus 1 over lambda, which is just e to the gamma over pi delta. We saw that E ground state minus E normal divided by L cubed, which is the energy density of the condensate, is equal to so it's negative, of course, otherwise the superconductor wouldn't form. N of 0 divided by 2. Yeah. And then we started looking into the specific heat. I was about to compute the specific heat, but then I suddenly remembered that I didn't compute the density of states. So let me compute the density of states. This is kind of a very simple task. All we really need to do, mu of epsilon is just the sum over k states. Sorry, 1 over L cubed, sum over k states, delta of epsilon minus Ek. This is really all we need to compute. This will give us the density of states. So we write this as an integral. We get 1 over 2 pi cubed times 4 pi kf squared, the integral dk of sorry, no, let's not write it like this. Let's write the integral dk k squared of delta of k minus wait, how do I want to do this? Hold on. Not go away from my notes because then it's going to become a mess. Okay, let's I see. Okay, so let me write this as square root of VF K minus KF squared plus delta squared. Now let me define this guy as some x. Okay, so then we have an integral of 1 over 2 pi cubed when we make the and let's do the integral around kf. So the Jacobian will give us kf squared. Then from the transformation, this factor of vf will give us 1 over vf. Let's also do the integral over the solid angle over the entire sphere because everything is spherically symmetric, and we get 4 pi. Okay, and now we're ready. We have an integral we have a factor of 2, so it's basically from minus omega dpi to omega dpi dx delta of epsilon minus square root of x squared plus delta squared. Okay, now this guy altogether is just the density of states. That's what we get, the density of states of the without the superconducting state. Yeah. Okay. So we get n of 0. Now let's take the integral just from 0 to omega dpi. So we get a factor of 2. And now let's change this to be a delta function over x. So this just becomes x minus the square root of epsilon squared minus delta squared. But because this is a delta function of a function, then we have this factor of x divided by square root of x squared plus delta squared. Okay, and this whole thing is dx. Now we just substitute this in here. And first of all, you can see that if epsilon is, you can even see it here, if epsilon is greater than delta, if epsilon is greater than delta, then there is no x that will satisfy this delta function. So it's automatically 0. So this immediately tells us that sorry, the other way around. If epsilon is smaller, if epsilon is smaller than delta, there is no x that will make you satisfy this equation, and therefore we're going to have a theta function. Okay, everything for epsilon smaller than delta is 0. So therefore we don't need to worry about this here. That can be complex or imaginary. So then we just substitute and we get 2 times n of 0 epsilon divided by square root of epsilon minus delta squared, epsilon squared, sorry, and times theta of epsilon minus delta. Okay, so what you can see here is a divergence. So it looks like this. Say this is a, I don't know, kx or something. Okay, one of the k's. It doesn't even matter because the whole thing is spherically symmetric. And then here we have a, not k, sorry, this is epsilon. What am I talking about? This is epsilon. Here we have delta, here we have minus delta. Okay, and then everything here is basically 0. And then it jumps like this. Okay, and we can also compute this. I'm not going to do it now. And here we have square root divergence. Okay, and this is, and if we divide this by the normal state density of states, then see this is 1. So basically it saturates to 1. Now what is this divergence? This divergence comes from the fact that this dispersion that you see here, it has a minimum on a sphere, not at a point. Okay? So typically, if you take a parabolic dispersion and you look at the density of states close to the bottom of the dispersion, okay, then we have, we can look at 1 dimension, 2 dimension, 3 dimension. What you'll find is that in 1 dimension it diverges like square root like here. Okay? In 2D it's constant. And in 3D it actually goes to 0 like a square root of epsilon. And the reason is because the density of states basically is telling us how much states are in a window, and as we take the window to 0. Now, if we look at the bottom of the dispersion, then you see, so for example, let's take a dispersion in 1 dimension, right? If I space, actually this is not okay what I did. Let's take, you see, let's try and take constant distance between these points and, plot a dispersion like this. And you see this point will land here, this point will land here, this point will land here, right? This point will land here, and that's it. So you see, so if I take a small window, you see you have more states here than as you go up because it's curving upwards. That's basically the origin of this thing. Okay, that's why it diverges like a square root at the bottom of the map. Now, if you have multiple dimensions, you have to remember that it is true that near the bottom the states are denser, but as you go upper, then the radius of this dispersion is also growing, so you have more states. So in 2D, for example, it's exactly enough to just compensate between the two. In 3D, it's already growing faster than it's growing faster than how much the states are becoming more dilute. Now, what is happening here? Here we're in 3 dimensions, and still it diverges like a square root. But the reason is because you see, once the minimum is on a sphere, it essentially goes back to a one-dimensional problem, right? Because you can just imagine, or if you like, the dimensionality issue, the fact that as you kind of grow, increase the location of the energy window, the radius of this sphere that you're taking is growing. Here it won't work around the minimum because the whole minimum is already on a sphere. So basically, in that small window around delta, you already have this increase in density. So it's not, basically the minimum is not a point, but a sphere. This is useful knowledge because it happens many times. For example, I'll just give you a few useful examples. If you have Van Hoff singularity in the dispersion, which means that's when the dispersion is like, has one curvature along one direction, but the opposite curvature on the other. That leads to, in 2 dimensions, that leads to a logarithmic divergence. There are certain models known as the Rashba, like spin orbit coupled models near the bottom of semiconductors that lead to, in 2 dimensions, to a minimum of the dispersion on a circle, which again leads to a square divergence. And these divergences can be important for all sorts of things. For example, if there's a square divergence, it typically means that the states down there are extremely susceptible. So every small perturbation can cause a modification. In the case of Bogoliubov excitation, it turns out that it's very hard to make Bogoliubov excitations interact with each other. They're kind of very weakly interacting. But if they were to be interacting and you would somehow excite them, which is also a question, like how do you excite them to be a degenerate gas? Because typically the way we excite Bogoliubov excitations is thermally. We add temperature and then they're like bubbling, but you see then the temperature is much larger than their Fermi energy. So they're like classical gas. So there are all sorts of questions, but these can be important. Second thing is that this density of states can be measured. So I should mention that it never looks ideal, like it never really diverges, right? What really happens is, first of all, temperature smears it. So we can do the same computation at a finite temperature. I'm not going to do it now. And then what you get is you get something like, you see, you kind of fill in the states, and these things are called coherence peaks. Coherence peaks, okay? But there are other things that can also smear the coherence peaks. For example, disorder. You have disorder. I won't have time this year to teach it, but there is a Abrikosov-Gorkov theory. You can, if you put pair breaking disorder, then you would smear the peaks as well. You can have variations in TC in the sample that will also cause a smearing of this at finite temperature. So there are all sorts of things that can smear these coherence peaks.
Also, you can write with impurities.
Yeah, that's what I was saying. Disorder. Impurities is disorder. Okay? So this is the density of states. Now let me remind you what we were talking about when we stopped last time. It was specific heat. So one of the most striking observations of superconductivity, beyond the absence of resistivity or the drop of resistivity to zero, all this effects of levitation, vortices, Meissner effect, all this stuff. Then another phenomena, you can just measure thermodynamic quantities like the specific heat, and it has a very distinctive feature. So let's talk about that feature. So CV, which is the specific heat at constant volume, is given by minus, is given by ds dt, t, no, it's t times ds dt, which is equal to minus t d squared f to dt squared, where f I wrote last time, f is the free energy of a free Fermi gas in units of K Boltzmann. So K Boltzmann is 1, is 1 minus n Fermi Dirac of E K ln of 1 minus n Fermi Dirac of Ek plus n Fermi Dirac of Ek ln of n Fermi Dirac of Ek. Okay, and then we saw that S is then given by 2 times the sum over K sec squared of Ek over 2t divided by 4t squared Ek squared minus t over 2 d to dt of delta squared. Now another thing I didn't plot last time is that one can also solve the self-consistency equation for delta at any temperature. So last time we solved that this is at 0 temperature, and then Tc was obtained by solving it at Tc, where it's 0. But you can solve delta of T as a function of T, where this is the this delta of 0, and this is Tc, and it basically looks something like this. Okay. And what you can see is that at small temperatures it's almost a constant. Okay, and why is that important? It means that if we look at T much smaller than Tc, then this term is basically 0. So we can then define epsilon as equal to Ek, okay, and make a change of variables. And then one gets that Cv is equal to 2 times the integral from delta to the square root of omega d pi. So we're cutting off the integral at omega d pi squared plus delta squared sec squared of epsilon over 2t divided by 4t squared epsilon squared. And then because we made the transition from integral over k to integral over ek, we can just use the density of states we already have, which is this density of states, and that's why we start at delta integral. Okay, and this thing gives us a delta cubed n of 0 divided by 2t squared square root of pi t over 2 delta times e to the minus delta over t. So what this tells us, it tells us that the specific heat at very small temperature decays exponentially with delta over t. Okay, so that's the first result. Now what we can do is go to a t of the order of Tc, okay? And then we start with t greater than Tc, right? If T is greater than Tc, it means that delta of T is basically 0, right? Because we're above the superconducting order. And let's call this Cv plus. So Cv plus means slightly above Tc. And if we look at this expression here, then basically all the Ek are just epsilon. This we can again neglect because delta is 0 and so is its derivatives. So then one gets Tc because we're very close to Tc. N of 0, the integral from 2 times 0 to omega dpi over Tc x squared. Here x is the same x as before. X is is Ek divided by 2t. Okay. It's Ek divided by Tc. This is what we're going to take. Okay, and this Ek goes up to omega dpi. This is our cutoff. Sec squared of x over 2. Okay, so this is just this. This is this. Where do we get? So we have. Let me see. So we have a t squared here, but this t squared with this t squared together gives this x squared, and then we have a dx, but to give dx units of energy we have this dc. Okay, and the density of states takes us from an integral over energy to an integral over k, which is what we started with. Okay, so if there are any questions, stop me. But this is what we need to compute. And then we can use the fact that we can take this to infinity because omega dpi is greater than Tc, or at least when omega dpi is greater than Tc. And that's the weak coupling limit anyway we take this. And then we take advantage of the fact that the integral from 0 to infinity x squared over 4 sec squared of x over 2 is equal to pi over 6. Pi over 6. Okay, so then this thing becomes Tc, density of states, wait, sorry. This is pi squared over 6. Pi squared over 3. Okay, so n of 0 pi squared over 3 is what we call gamma. It's not the gamma we had in the last class, which was the Euler's constant. This is called the Sommerfeld coefficient. Okay, so this is something known from Fermi liquid theory. If you have free fermions, or if you have a Fermi liquid, because it has a Fermi surface, it has a constant density of states. The constant density of states leads to a specific heat which is linear in T. Okay? Basically the change in entropy with temperature is linear in temperature, and this coefficient is known as gamma. This is a very distinctive feature of fermions. So just as a side comment, people measure specific heat of all sorts of materials, and it's always so for a metal it's trivially linear. It's very easy to measure. well, in general, measuring a specific heat is not that easy, but given that you can, today there are built, factory-built devices that do that inject some sort of heat abruptly, and then measure how it's dissipated, and from that they kind of know the specific heat. But people measure a linear and specific heat many times in all sorts of materials where it's not expected. So insulating materials in particular. And that's always very interesting, because then people speculate. But I should point out that the only thing you really need to get a linear and T-specific heat is that the density of states is constant at low energy. Okay, the Fermi C gives you that because even when you freeze it, okay, it's not like a boson system where you just lose all the bosons or something. You have a gap or something like that. And I'll talk about bosons in a second. But because you have a Fermi C, then the density of states is constant. Now, if you take bosons, for example, like phonons contribute T cubed. So that's also a way in which people distinguish between the specific heat coming from the fermions and coming from the phonons in the crystal. Okay, so that's C plus, but now let's compute CV minus. Okay, so CV minus, you can notice the only difference really is this factor. So this guy, because we're very close to TC and delta can be neglected, delta is tiny, 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 then this whole integral will give the same thing. So it's just going to give CV plus minus this term. So we're going to have a density of states to the integral from 0 to omega d by the epsilon sec squared of epsilon over 2 Tc divided by 8 Tc d to dt of delta squared. Now this thing, later today I will show you that this guy is equal to minus 8 pi squared over 7 zeta of 3 Tc. Okay? We'll see that. And this integral turns out to give, I'll tell you in a moment, hold on. 4 pi, wait. Just let me get this straight for a second. Ah, yes, yes. Okay. Yes. Okay. So what this tells us is that CV plus minus CV minus is equal to 4 pi squared divided by 4 pi, no, wait a second. 8 goes with that, so it's probably 2. 2 pi, where is the extra factor? Maybe this integral gives 2. Probably this integral gives 2. Don't, we can fix that later. zeta of 3, n of 0, tc. Okay? But now we can use this factor is, so I can multiply and divide by gamma. Okay, so I can put here gamma and gamma. But here I can put the gamma to be, you know, n of 0, pi squared, and I have a 3 here. So this then cancels with this cancels with that, and we have 12 times tc, 12 7 zeta of 3 times gamma tc. Okay, so it basically tells us that there is a jump in the specific heat if you're slightly above tc, or slightly, oh sorry, this is the other way around. This is minus and this is plus, because the minus is of course bigger because this derivative is negative. This derivative, by the way, is, you know, it's related to how, so remember that I drew before delta of t as a function of t, where here it was tc. So if we plot this squared, you'll find that it comes out linearly. Okay, so it starts as a square root delta, so the square goes like linearly, and this slope here is exactly minus 8 pi squared divided by 7 zeta of 3, and believe it or not, we're going to compute that in a second, times tc. Okay, so this is the slope. So yeah, so what does this tell us? It tells us that if you look at the specific heat slightly below tc, slightly above tc, there's going to be a jump.
So it's a first order phase transition.
No, it's not a first order phase transition, because you have to be careful. In fact, the superconducting phase transition is it's much more complicated. We can't classify it in the same way we classify so let's start from the superfluid transition. So if you would have a superfluid and it would be neutral, then it's a second order phase compression, right? That's standard. Now let's charge the superfluid, because this is what we have. We have a superfluid which is charged. Okay. Then if you charge the superfluid, you're going to get a topological phase transition. So there is no order parameter. Now, what happens to the specific heat? If I would just look at a charged, like, I'm not used to thinking about this, but probably, think about this for a moment. I am guessing you would have no distinctive feature in the specific heat. Okay, you can also ask what happens when you look at the superfluid, the neutral superfluid of the transition. What happens to the specific heat? This is known as the lambda point, because the specific heat looks kind of like a lambda. So I know that there's a cusp. Maybe we should have calculated it, but now what you have is on top of this topological phase transition. And what do I mean when I say topological phase transition? What I mean is that the transition is between two states with the same symmetry. Remember that when we're talking about a superfluid, the order parameter was associated with number conservation. For phase, the order parameter was the phase. Okay, so we had a U1 symmetry, which is global gauge invariance, and we chose a specific phase. But here, because we have local gauge invariance, then the phase above and below TC, it's the same. There is no distinction. So in that sense, it's a topological phase transition. You cannot distinguish the superconducting state from the normal state based on an order parameter. Okay, it's some other classification, some higher classification, And this goes into the field of topological phase transition. And specifically in this system, the situation is even more complicated because this bosonic liquid is actually coming from a liquid of pairs, fermions. And they're the ones that are contributing this jump in the specific heat. So I would not distinguish this. I wouldn't classify this as a first order phase transition.
Right.
Okay? Yeah. And and to be honest, when we say first order phase transition, we mean that the now, finally, I need to correct you because what you said is actually wrong. Why is it wrong? Because the relevant thermodynamic potential in a first order transition has a cusp. That means that its first derivative will have a jump.
Right.
Okay, so that would be like a jump in the entropy or a jump in the volume or something like that. That's for liquid gas transition. What happens? There's a jump in the volume, right?
Right.
Here, this is a jump in the specific heat, so that's similar to a second order phase transition, right? Because what's a second order phase transition? It means that the derivatives, the second derivative of the associated thermodynamic potential has a jump. But still, I wouldn't call it a second order phase transition because it's more delicate. But let me summarize the result here. So what we find, and this is also a very famous result, which is
so just what the deep reason is that we don't have actually like in liquid in superfluid we don't have we don't have spontaneous symmetry breaking. We have the Anderson mechanism, and that's the reason why it's not actually a phase transition.
It is a phase transition. It is a phase transition,
but not easy to.
But it's not described by a Ginsburg-Landau theory. It's more delicate. Okay, so now if we plot CV over gamma T, okay, versus T, and here we have TC, here we have basically 1, okay? So above TC we expect it to be more or less constant, and then here we have a jump. The size of the jump is exactly this 12 over 7 zeta of 3, which comes out to be 1.43 something. Okay, so this jump is actually larger than this. So it's a big jump. And then it goes down. And here we saw that it goes like e to the minus t over delta, which is what is written over there. Okay, so this is the result. So we basically have at least collected two very, very sharp, testable predictions of VCS theory. The first one is that Tc over delta is equal to e to the gamma over pi. And the second one is that delta Cv, the jump in the specific heat, is 12 over 7 zeta of 3. Which is quite amazing if you think about it. This is like, for anybody writing a theory, this is the kind of things that you want to produce. This is like, you know, you can just go to an experiment and measure. This is like a very, very sharp prediction. Okay, and the amazing thing is that for metals, almost all of them agree with this. So when people say that, you know, VCS theory works, this is what they're talking about. These guys started from a very simple model, very simple assumptions, and go all the way to these expressions, and then you go to experiment and it works. Okay? It works perfect. And I don't know of many examples in theoretical physics where people got to this level of prediction. Okay? But what's interesting, and that's the reason I have a job, is that there are families of superconductors that completely violate this. Okay? Which are not BCS. Their starting point is not it's not valid to use BCS, and there are many other examples why BCS doesn't work. But for example, one of the things is that these kind of expressions don't work. Okay, so with this, I'm done with BCS theory, and I move to the next part, which is the last part that I'll teach you. Unfortunately, this is what I will manage this year, and that's so we saw two. I like to call it like two pillars, two like amudei tavuk that the theory of superconductivity is standing on. And now the question is how to connect. Okay, because the Ginzburg-Landau theory was completely phenomenological. We just wrote parameters. Okay, BCS theory is extremely microscopic. Like you just well, it's microscopic. Also, there you could say that the strength of the interaction is something that we don't know exactly, but at least given some specific some specific density of states, Fermi velocity, etc., and some specific interaction, what would be the Ginzburg-Landau theory that results from this theory? And this is what we're going to answer today. And we're also going, from this, we're going to get this relation along the way. What is this? So we're going to use something known as the Hubbard-Zlatonovich transformation, which did we already do the Hubbard-Zlatonovich transformation? I don't remember. No. Okay. Do you want to take a break now? Maybe now is a good time to take a break. So we can come back at 4 and 5 minutes. Is that good?
Break. This has to be a very easy result to get in the theory, right?
What?
That the CV below TC.
Yes.
It seems like a field integral, right?
Field integral. Well, how do you see that it's
like I don't know the structure of the negative exponent over delta and the square root.
It's just a generic. Just a generic situation that you're thermally, like, all the entropy you get comes from excitations,
right?
And because in this case you have a sharp gap, okay, then the only way you can excite is thermally. But if delta is much smaller than if TC is much smaller than delta, then you're living on the exponential tail.
Okay.
Right, and that's the origin of this E minus delta over T. It doesn't have anything to do with. The things are, of course, related because you could ask, okay, where does the Boltzmann factor come from? Boltzmann, when he derived statistical mechanics, he guessed that the probability of some state should go like this.
Right.
But given that this is correct, the field integral comes from that, because how do you write the field integral? We write e to the minus h over t and take a trace over it. So that's where it comes from. So they just both come from the same origin.
Yeah, sure. Yeah, it has to be like it's constructed in that way.
Right.
Thank you.
איתן, נכון?
נמרוד.
נמרוד. אתה דיברת איתי על לעשות פרויקט?
מחקר.
מחקר. ואני כבר... הסמסטר הזה אני איבדתי את זה לגמרי. אנחנו כאילו לא נפגשנו מאז? מה...
שלחתי לך מייל, אבל לא ענית.
אוקיי.
ומה שאלת במייל? רציתי לקבוע פגישה לגבי מחקר. כאילו נכנסתי קצת לנושא, קראתי את הספר...
אבל דיברנו על בעיה?
כן. על ההתנגדות של שינוי בפאזה של סופר פלואידיטי, של המקור של...
סטיפנס.
כן.
אני חושב את הסטיפנס של... אוקיי, בסדר. אז מה צריך לעשות? אז תראה, האמת, אולי הדרך הכי טובה, אני יכול לשלוח לך כמה מאמרים שעשו את זה לאחרונה. עשו את זה לאחרונה. האמת שאם נספיק היום, אולי אני חושב על סטיפנס, אבל לא נראה לי שאני מספיק. אבל יש כמה מאמרים שעשו את זה לאחרונה, מאוד מתלהבים מזה, כי יש איזשהו סיפור אני אסביר, הצליחו, אז יש חומר כזה שנקרא גרפין. שמעת על החומר?
כן.
גרפין הוא כביכול, זה שני פסים שנוגעים אחד בשני בגלל סימטריה בנקודה, שתי נקודות בעצם, שזה נקרא דיראק פוינטס. אז זה חומר שמאוד מאוד אוהבים אותו, קודם כל הוא מאוד מאוד נקי. אפשר לבנות ממנו devices, והחלקיקים בו הם חלקיקים כאילו, הם מגיעים כמו חלקיקים יחסותיים, בלי מעשה. אז נורא אוהבים את זה. עושים את זה כל מיני משחקים. אחד מהדברים שאף פעם לא הצליחו לעשות זה לגרום לזה להיות מוליך על. כלומר, גילו את זה ב-2004. זה גם סיפור מעניין, כי חשבו הרבה שנים שלא יכול להיות. כי יש מה שנקרא מרלין-וגנר תיאורם. מרלין-וגנר תיאורם מראה שהפלקטואציות של spontaneous symmetry breaking מתבטרות בדו-ממד, ולכן כביכול אין סדר בדו-ממד, ואז קבעו שלא יכול להיות גביש דו-ממדי. אבל אז הם פשוט הראו שיש גביש דו-ממדי. זהו. אז הם הראו את זה ב-2004. אחר כך ב-2010 הם קיבלו פרס נובל על הגילוי הזה.
על זה שהוא בכלל גביש, או מה הכוונה?
לא, הם מדדו שם תכונות אלקטרוניות, והתכונות האלקטרוניות הוכיחו שזה גביש דו-ממדי. על הקיום של הגביש הזה, קודם כל, הם גילו איך לעשות את זה, זה סיפור מאוד מצחיק. הם לוקחים גרפית, שזה כמו גז'ש בעיפרון, ועושים את הסלוטייפ הזה, שמעתם את השטות? באמת, לוקחים סלוטייפ?
אתה אומר על מג'יק אנגול?
כן, אני מתחיל להסביר על זה. עושים סלוטייפ ואז לאט לאט מתקלפות חתיכות, כי החומר הזה הוא בעצם גבישים דו-ממדיים שהם נדבקים אחד לשני בתקופות ואנדר ואלס. כן, תדמיינו שנכון אתם מרטיבים קיר ואז אתם מדביקים ספוג או משהו שזה נדבק.
כן.
כן? אז פה תדמיינו שיש לכם נייר שהוא כל כך דק שהוא שכבה חד אטומית. אוקיי? לא שכבה חד אטומית. שני דברים כאלה נדבקים אחד לשני בצורה שכאילו אי אפשר להפריד. זה לא שאתה תופס את זה, זה גילו איך להפריד את זה. זה בעצם מה שהם גילו. אז רק על הגילוי הזה ועל זה שהם הוכיחו אחר כך שזה באמת זה בשביל הם קיבלו פרס נובל. אז כל הזמן החומר הזה לא מפסיק להפתיע. כל פעם אתה אומר, טוב, זה מת, אין יותר עוד מה לעשות פה. אז אחד הדברים שבאמת אף פעם לא היו זה מוליכות על, אף פעם לא הפך להיות מוליך. ומצד שני היו אנשים שחשבו שאפשר כאילו לקחת שתי שטרות כאלה ולסובב אותם אחד ביחס לשני. אז אפשר לקבל, מה?
ואז יהיה מוארי פאטרן?
ואז יהיה מוארי פאטרן. והמוארי פאטרן זה כמו מין סופר לטיס, זה לטיס על לטיס. אז כשהם עושים זווית מאוד מאוד קטנה, אז הפיריוד של הלטיס הזה מאוד מאוד ארוך. מי שבאמת חשב על הדבר הזה ראשון, דרך אגב ישראלי, שעשה את זה בפוסט שהוא היה באוסטין, קוראים לו רפי ביסטרצר, הוא עכשיו עובד ב-Applied Materials. הוא לא קיבל משרה בארץ, הוא חיפש משרה, זה היה אחד מהעבודות שהוא עשה בפוסט, אבל לא קיבל, הוא התראיין גם פה דרך אגב. החליטו שהוא לא מספיק אסרטיבי, נערף, לא יודע. ואז ב-2018, כשהייתי ב-MIT, הם הצליחו ליישם את הדבר הזה, והם גילו שזה בעצם הופך להיות מוליך על, ועוד עושה המון דברים מעניינים אחרים. והרעיון הוא, הסיבה שזה עובד, זה בגלל שהפסים שמתקבלים, כשזה מאוד מאוד דק, שזה נקודת קסם כזאת, שבה אינטרלייר הופינג והאנרגיה בדיוק מתאים כאילו אפשר לדמיין שיש שני דיראק פוינטס כאלה שההבדל ביניהם קשור לזווית סיבוב, והגובה פה באנרגיה הוא משהו כמו פעמיים VF כפול הדלטה K הזה, זה דלטה K, ומצד שני יש את האינטרלייר הופינג שהולך כאילו בעצם לגרום ל-avoided crossings פה ופה, הוא הולך לדחוף את זה, בעצם להפוך את זה למשהו כזה, כאילו פה יש עוד איזשהו פס ופה זה כאילו שני T. אז כששני T הזה בערך מסדר גודל של הדבר הזה, אז מקבלים פס שהוא מאוד מאוד שטוח. פס שהוא מאוד מאוד שטוח, זה בדיוק כמו ה-density of states שדיברתי עליו קודם, יש המון density of states, ועכשיו כל דבר יכול לקרות. אז גילו שם מוליכות העל, ואחד מהדברים שהם באמת דיברו עליו זה, לא נחשב היום את הסטיפנס, אבל אנחנו כבר ראינו בתחילת הקורס שהסטיפנס הוא בעצם, הוא ה-superfluid density, כאילו כמה חלקיקים נמצאים בקונדנסייט, לחלק לשני M. אז המסה בעצם, היא בעצם קובעת את הסטיפנס. כשהמסה היא ענקית, הסטיפנס הוא קטן. כשהמסה היא קטנה, אז הסטיפנס הוא גדול.
אבל לא אמרת שזה מתנהג כמו חלקיק יחסי חסר מסה?
נכון, אבל זה בדיוק העניין, שאחרי שאתה עושה את זה ככה, קודם כל כשאני אומר 2M, אני מתכוון מין מסה אפקטיבית. לא משנה, אבל פה בסוף אתה מקבל איזשהו פס שהוא נראה ככה, ואתה יכול לחשוב על מסה נגיד מפה, מהגבול העליון, אתה לא חייב ביחס לנקודות האלה שזה באמת נשאר דירה. אפשר להגדיר את זה, אבל הרעיון הוא שמסה מאוד, פס שטוח אומר מסה מאוד גדולה, מסה מאוד גדולה אומר סטיפנס מאוד קטן. אז על פניו הסטיפנס בחומרים האלה אמור להיות מאוד מאוד קטן, ואז לא ברור איך הם נהיים מוליכי על, כי אם הסטיפנס שלהם הוא מאוד מאוד קטן, הם מאוד שבריריים. גם בקורס הזה הסברתי שאפשר לחשוב על הסטיפנס כמו שיר מודולוס של גביש, שמזיזים אותו ככה, כן? אז אם הסטיפנס הוא מאוד קטן, זה כמו גביש כאילו שאני מפעיל עליו מעט מאוד כוח והוא זז המון, הוא נשבר בקלות, גם זרם קטן הורס. פחות או יותר זה הסיפור. אז בחומרים האלה נורא הם גילו שיש עוד תרומה לסטיפנס שמגיעה internal structure של הבנדס, שזה מעבר
מהטופולוגיה שלהם כאילו?
משהו כזה, כן. ואפשר לחשוב על זה שהווקטור של המצבים ב-K-Space הוא כמו מרחב וקטורי אחד, והברילואנזון הוא כמו טורוס, אז זה כמו העתקה של איזשהו וקטור מהטורוס, כאילו זה העתקה מהטורוס למרחב הוקטורי של זה, ואז יכולים להיות לזה, עכשיו במקרה הזה אין לזה קלסיפיקציה טופולוגית, קלסיפיקציה טופולוגית היא טריוויאלית, אבל יש לזה משהו שנקרא fragile topology. זה סיפור שלם בפני עצמו, זה סיפור מאוד מסובך, אבל כן, זה לא בדיוק הטופולוגיה, אלא העובדה שיש שם הרבה היברידיזציה בין האורביטלות השונות, שהיא בעצם גורמת לדבר הזה. אז אני אשלח לך את המאמרים האלה, וזה יהיה starting point טוב בשביל
מה זה עובר פאזה למוליכה?
מה זה מה?
מה המעבר פאזה של הגרפן? הוא סמי קונדקטור לפני שהוא הופך למוליכה?
לא. קודם כל הוא מה שנקרא סמי-מטל. זה העולם שלנו קסום. כי סמי-קונדקטור זה בעצם מתכוונים לאינסולטור. וסמי-מטל, שזה נשמע כמעט אותו דבר כמו סמי-קונדקטור, נכון? כי קונדקטור זה מטל, מה ההבדל? זה משהו אחר לגמרי, שזה סיטואציה שבה בעצם יש קרוסינג בין הפסים. כשיש קרוסינג בין הפסים זה בעצם אומר שלא משנה איפה הפרמי אנרג'י נמצא, הוא חייב לחתוך gapless states. וזה מה שקורה בגרפין, אפילו כאילו תמיד מוליך. אם אתה בצ'ארג' נוטרליטי, אז יש לך מתכת מיוחדת, זה נקרא דיראק מטל. זה לא פרמי ליקוויד רגיל. פה זה הרבה יותר מורכב, אבל בגדול זה משהו מתכתי, אבל האינטראקציות מאוד מאוד חזקות בו, אז אפשר להגיד שזה strongly correlated metal. אז בואו נתחיל. רגע, מה אני רוצה להגיד? Hubbard reach transformation. So in every field they have a different name for this, which is kind of funny because it's a very fancy name for completing a square. The idea is, imagine that we start with an interaction, our BCS interaction. So before I wrote a Hamiltonian, but we already saw in this course how to cast Hamiltonians into actions in a field theory on which we perform some field integral. So let's assume that we did that, and now I'm writing the interaction part. So the interaction part is local, space and time. And so it's something like this. Okay? V is the strength of the interaction. Now notice that this is, so this comes from, so, Z is equal to some field integral over C dagger and C. Okay? E to the minus S0 of C dagger and C. Minus S interaction of C dagger and C. And this thing, this guy here, is exactly e to the minus S interaction. This is just what I wrote. So without the piece of the integral, so this goes inside. That's it. Okay? Now, what I want you to notice is that because of this minus sign, if it's positive here, that implies an attractive interaction. Okay, and this is crucial because we need the interaction to be attractive to perform this transformation. Now, the Hubbard-Satonovich transformation is going to take us from an action which is a quartic in the fermions to an action that is quadratic in the fermions. But the price we're going to pay is that we're going to add another boson field which these fermions are going to interact with.
This is similar to how we start working with the tightly binding lattice?
No.
No?
Why? How is it related to a tight binding lattice?
With this interaction with
I see. So you're saying when we do tight binding, you're thinking about it like this. When you do tight binding, then you see that on each side you diagonalize the local Hamiltonian into orbitals, and then the hopping between sites is taken as a perturbation of the interaction.
when we
right?
Yes.
That's what you mean. No, no, no. What we're doing right now, unlike that, is exact. We're not going to throw away anything.
So no
Okay.
mean field. or
No
anything.
approximations. Okay?
That's the thing that you can do through like the direct channel, corporate channel. This is the same.
So when we do the Haber-Safronovich transformation, we need to choose. That's kind of the point. The point is that we need to choose how we call it how to decouple the interaction. Okay. So what we're going to do is I'm going to write this exponent as an integral over a bosonic field. Okay. What do I gain from this? The action is going to become quadratic in terms of the fermions. What is the price I pay is that I need to add another bosonic field, which the fermions interact with. And you can think about this, if you like, as, it's the same thing like in QED. Right? If you have fermions that are interacting with Coulomb interaction, we know that you can write a version of it, which is what we believe is the right way to write the action, where the fermions are actually, the action is quadratic, but there is an interaction with the gauge field. And we know that a quadratic action of fermions plus a coupling to a boson is no longer a non-interacting model. It's because of the... Okay, so that's kind of the philosophy. But as you'll see in a moment, we need to choose how to do this, and I'll talk about this in a moment. But so what we can write is that this thing is equal to 1 over z delta, the integral of d delta bar and delta, e to the minus, okay, so here we have an integral from 0 to beta d tau, an integral d dx. Now I open minus delta squared over v plus delta c dagger up, c dagger down, plus delta c down, c up. Okay? Now why is this true? Because you could imagine that I can rewrite this this guy, everything in here, I can rewrite as delta bar. I can write it like this: minus c dagger up, c dagger down, v to the minus 1, delta minus c down, c up. Maybe let me write it like this: v c down, c up. Okay, minus plus v c dagger up, c dagger down, c down, c up. Right? So this is what I meant by completing a square. So now we have a new action. So our new action. And now the point is that this thing, you can imagine just performing the integral. Now, because this, as far as this field delta is concerned, this is a change by some constant. Who cares? We can absorb it. It's just basically a Gaussian integral into the definition of delta. And this Gaussian integral will give you z delta.
So here you just introduce a resolution of the identity, right?
Well, it's not, I wouldn't call it resolution of the identity, because the resolution of the identity is the idea of an over-complete basis. Okay? Where we want to introduce, some a notion of the identity matrix, but in terms of some over-complete basis. This is something else. It's just the identity. It's just
Okay.
one. Okay.
Right.
You don't need to give it fancy names. So then what we get is we get a new action, which is the integral from 0 to beta d tau. And let me also write something here, that this S0 of C dagger and C, okay, this guy is an integral from 0 to beta d tau, an integral d dx of C dagger sigma, and then we have what do we have here? What do we have? We have minus d tau minus e phi plus minus I grad minus EA squared divided by 2m minus mu. Sorry. C sigma. Okay, so this.
Summing over sigma.
Yeah, there's a sum over sigma. So this thing is what we call G electron to the minus 1. So now where this fancy psi is written in the particle hole basis. It is known as Nambu space. Okay?
It's spinal.
It's what?
Is it spinal?
It's a spinner. It's a spinner. But to be honest, we could have written also this in terms of spinner. Here we have no spin orbit coupling or anything interesting, so it would just be diagonal. But yeah. But the nice thing is that as long as we're looking only at so before you were asking about the decoupling channel. Here we chose the decoupling channel. See this delta? Oh, by the way, this is delta bar. This delta here couples to a pair operator or a pair field. This pair field is a singlet pair field. Okay? It means that we're assuming that they pair in an S-wave state, which is singlet. And we took it in the superconducting or BCS channel. We don't have to do it that way. We can do it in different ways. For example, you could do a magnetic decoupling. You could assume that you have some field M, magnetization, which couples to something like, you could do a decoupling like this. Okay, you could do a decoupling like that. You could do a decoupling into the density channel. You can do whatever you want. And it's all accurate. We didn't do anything inaccurate. Okay, we didn't throw anything away. So remember that for later we'll discuss exactly what does it mean to choose a specific channel in a second. I'll describe this in a second.
Yonathan, what makes it specifically the singlet and not the part of the triplet that is also up, down, and down, up?
Because because you can always write C down, C up as 1/2 C down, C up minus C up, C down.
And the other way around. No. And the other one is plus. Right, okay.
So the point is that only when you're talking about singlet, you can compactify this so nicely. If you go into the triplet basis, you'll always have to write it in some sort of matrix. Moreover, this spinner that you see over here, you cannot write it when you deal with triplets. With triplets, you have to write the 4x4 space. And then there's another interesting question, which is the fact that there is some redundancy, right? Because here, okay, let me explain what I mean by that. So this G0 to the minus 1, okay, it's going to be right, we're going to have d tau minus d tau where is this one? Okay. Minus I grad minus EA squared divided by 2m minus mu. Here we're going to have minus d tau minus I grad or plus EA, I guess. Okay, let me see in a second. Okay, so what you see here is that basically this part is the inverse Green's function of the electrons with spin up. This part is the inverse Green's function of actually the holes with spin down, because of this structure that you see. If you would want to write it in terms of triplet, you would need to include everything, and you would need to have, you know, this spinner would look like this. It would look like C up, C dagger up, C down, C dagger down, something like this. It would need all of them.
Like Dirac matrix has?
It's you know, it's a 4x4, but. And of course it can be related to Dirac matrices, but the important thing is that we would need to include both. So you'd have twice this and twice that, once inverted each time. And this would be a 2x2 matrix. This part would be a 2x2 matrix representing exactly the singlet and triplet parts. Okay? Now, then you would have some sort of redundancy, because you would actually count twice. You would do this once and then the other one once. And there's a whole formula, there's not a whole formalism to itself, but one can still solve the field integral in this case. The issue is that then the determinant, you know, you'll see in a moment that there's going to be a determinant. It turns out that then the determinant needs to be replaced by a Pfaffian, okay, which is something like the square root of the determinant, which is an interesting fact, and I might give you an exercise on that. Actually, I need to give you another exercise. No one handed in an exercise. I guess I don't really know what I'm going to do with this course anyway, but that's fine. Okay, so now the point is that we have this action, and what we can do is we can just Fourier, not Fourier. One thing is that, okay, we could Fourier transform this. This is another issue, which is sometimes much more convenient. So you could imagine that instead of thinking about this psi dagger and psi in real space, we can also write this in terms of k and omega, and then we have minus I omega plus so if there are no magnetic or electric fields, then it's useful to do this Fourier transform, and then everything becomes much simpler. This is actually all we're going to use today. So this is a matrix between, this would be like K, and this would be like K prime, and then this is a matrix of K and K prime, and we sum over.
This is after Fourier transformation?
Yes. So that's just a comment. But the point is that if you look at this action, it's quadratic in these fermions. So that means that we can integrate them out. We can just perform the field integral over these guys. And I remind you, what
happened to the magnetic potential?
Okay, so then we get that Z is equal to the integral d delta bar delta times the determinant of this g to the minus 1, right? Because it's just the determinant of the matrix. This matrix, by the way, is diagonal in actually, it's not diagonal in anything. I shouldn't say it's diagonal. It's diagonal in all sorts of stuff, but I don't want to get into the details. This is a matrix in K and K prime. And by the way, when I say K and K prime, these are 4 vectors. So like K is equal to I omega and K vector or something like that. Because it's you see it's a matrix in all this space. And this Q here is same thing. This Q here, Q is something like, you know, I omega and Q vector or something. So this field, the point is that you have to remember that this field delta is a fluctuating field which we are integrating over. This is not an order parameter. It's not some constant or anything like that. Okay, so that's another issue. now we have this thing, and you see that this g to the minus 1 depends on these deltas. So they appear, and then we have e to the minus the integral d tau d dx of delta squared over v. Okay? Now, okay, I have to move. How much time do I have left? Like
50 minutes.
50? 50, okay. 50 we can probably manage. Now, this we can bring up to the exponent with a log. And we use the fact that ln of det of a matrix is equal to trace ln of a matrix. Okay? Now, this should be read in this way. The determinant of a matrix is a number. This is the ln of that number. Here, this is a different story. This is the ln of a matrix. What is the ln of a matrix?
Also a Taylor summation.
Yeah, you can imagine writing this. So you can write ln of a matrix as ln of 1 or something like, you know, identity plus A minus the identity matrix, and then you can expand this as a power series of sum over n equal to 1 to infinity of the matrix A minus the identity divided by n minus 1 to the n or something like that, right?
The a minus 1 to the n and this n plus 1. The minus 1 to the n plus 1.
Minus 1 plus 1. Doesn't matter. Same. Okay, so so you can make an expansion like this, and then imagine that you take this matrix and you take a trace of it. This is what this means. And this is the equality. Okay? So what that means is that we can write this z as the integral d delta bar delta of e to the minus the integral from 0 to beta d tau d dx delta squared over v minus a trace ln or plus, and if we're writing it like this, plus trace ln of this g to the minus 1. Okay? And this trace ln is the guy that we're going to live with. So the point is that now what we're actually going to do is we're going to say the philosophy is going to be the following. So, okay, so what this implies, okay, let me write it. So what this implies is that we arrived at an action of delta bar and delta, which is equal to an integral over tau and x of delta squared over v minus trace ln of g to the minus 1, where how we take this trace is something we'll have to learn in a moment how to do it exactly. But you understand that this G is basically a huge matrix. It's a matrix in the space of this particle whole space, but also a matrix in terms of the K and K prime, which we define in this manner. Okay?
So why is it better?
Wait a second. I don't want to talk about why it's better. I first want to describe what we want to do. So the point is that I want to remind you that we had an action, okay? We had in GL theory we had something like S is equal to the integral d tau d dx. Something like C delta bar d tau plus 1 over 2 eta, right? And I'm writing this in terms of delta deliberately and not psi like we had when we wrote the Ginsburg-Landau theory, and on purpose because I want to remind you that the Ginsburg-Landau field was something like density, okay, it was like the superfluid order parameter, it had units of density. Here we have delta, which in the theory it has units of energy. You see it appears in the Green's function, inverse Green's function. So they're not exactly the same thing. And one of the things that Gorkov did was map between the two, and we will do that later. So that I wrote it like this. But you identify, oh, shit. Two deltas. But you identify the general structure. Right? This is like a Ginsburg-Landau theory, like we had. And basically what we want to derive is what is C, what is 1 over 2 eta, what is R, what is U over 2. How do we compute these? And you see that here we have a mapping for that. For example, we already see that this 1 over V goes into R. Right? Because it's a coefficient of delta squared. But all the other terms will come from this trace log. So we can, what we're going to do is we're going to expand this trace log in small delta, and that's how we're going to derive these parameters. And with that, we're going to end the course. Now, the question, to your question, why is this better? Because it's all a question of a saddle point. Okay? Because if I take the saddle point, you'll see that if I take the saddle point of this guy, I will get the gap equation. So it shows me that the saddle point is BCS theory, is the BCS gap equation. And then I say, okay, let's assume in the spirit of mean field theory, I assume that I have an order and the fluctuations around this order are weak or small. Then it's the appropriate saddle. Okay? Up to now, when I wrote this trace log, because this is a log of a matrix and this matrix, it's a whole mess. Actually, it's a super complicated theory, and it contains all the information about the fermions somewhere hidden in these complicated, mess. But the beauty of it is that it has the right saddle, and that's the expertise you need when doing Hamburg-Suttonowitz. You need to choose the right decoupling. Okay? And that's actually one of the things that I'm in my research. I'm investigating, like Amir Dalal, my PhD student. One of the things that we were debating a lot was playing around with, what happens when you make a mistake? What happens when you choose the wrong coupling? How do you see, say instead of making a decoupling into the superconducting channel, I would do it in the density channel. How would I, sum up all the fluctuations of the density channel in order to get the superconducting instability? Okay, and that's like, if you like, that's an open question. We don't know exactly how to do it, but I have some ideas.
Does the decoupling channel have a physical interpretation?
Well, you see it does, because when you take a saddle point of delta, delta then becomes the order parameter at the saddle point. So if you look at delta, this delta of Q, delta is 0 at the saddle point equation is the equation for the order parameter. And you see also, I just erased it, but this delta appears like a field for the fermions, like a pairing field. But it shouldn't be, it's indeed true that one needs to be careful not to associate it with the mean field order parameter exactly, because it's not the same thing. It's actually it's a conjugate. But nonetheless, it's just a mathematical trick, right? We can do it, so we do it. And it's useful for us in a way that I'll show you in a moment. Okay, so now...
Does the action is a Lagrangian action or a Hamiltonian action? The action that you wrote here.
What is a Hamiltonian action?
It's in the books that sometimes they use the Hamiltonian action, sometimes they use Lagrangian action. I didn't fully understand the difference.
Maybe P and Q or Q and Q dots.
Yes, something like that.
So here you can see that in terms of that, this is obviously a Q and Q dot version because, okay, we will see in a moment, but we have like delta and the time derivative of delta here. This is like this. This is like delta delta dot. Okay, but so to derive the Ginzburg-Landau theory, I'm going to write this trace ln of g to the minus 1. So let me first write that g to the minus 1 is a g naught to the minus 1, okay, plus delta, okay, where g naught to the minus 1 is, it's like this g electron to the minus 1, g whole to the minus 1, 0 and 0. And this delta is equal to delta and delta bar. This, of course, comes with a delta k, k prime, delta k, k prime. And this comes with a delta k, k plus q, delta k, k prime, delta k, k prime minus q. Okay? And this is q. Sorry, this is not with a hat. This is okay. So now I can rewrite this as trace ln of g naught to the minus 1 plus delta, which I can then write as trace ln of g naught to the minus 1, a identity matrix plus g delta, g naught delta, which I can then write as this is a trace, and then write as trace ln of g naught to the minus 1 plus trace ln of identity plus g naught delta. This part we can just call it S0. This is the action of the fermions in the absence of the superconducting field. Or in fact it's the non-interacting action. Non-interacting
So it's like a fermion capacitor.
action. Yeah, it's uninteresting as far as we're concerned. The second term gives us this guy gives us by the way, I didn't show it because I don't have time. But you can trust me, and also look in Alfand and Simons, it's kind of trivial that if you take the derivative delta S over delta delta bar equal to 0, and here you take Q equal to 0. So you look for the saddle point at Q equal to 0, which fixes Q equal to 0. This will give you the gap equation. That we had before. You also need to do a Matsubara sum, because when we did the gap equation, we did it from BCS theory. It was in Hamiltonian formalism. There was no Matsubara sum. But here you need to do the Matsubara sum. After you do the Matsubara sum, you'll get exactly the gap equation that we had in BCS theory. So this thing gives us minus sum over n equal to 1 to infinity. So that's the same thing we had over there. Right, we have, okay, maybe we can just write, so we have minus 1 n plus 1 divided by n, trace of G naught times delta to the n. Okay, and now the idea is going to be to look at powers. I'll explain to you in a moment how to take this trace, but now we want to look at powers because, for example, the second power is going to give us exactly, you know, the quadratic terms, this, and this. Okay? Specifically for this, we also have this guy. The quartic term, the n equal to 4 term, is going to give us this. Okay? And by the way, one can find, also I'm not going to show because I don't have any time, that the odd powers of n vanish, which is very good because we need a gauge invariant theory. It wouldn't be gauge invariant if the odd terms would be fine. Okay? So that's also something important. So let's talk about how to do this trace. Okay. So, for example, 1/2 trace of G naught delta, G naught delta. Okay, you can think about these matrices as matrices in K and K prime space. And you already saw that this delta, it takes you from K, the K plus Q. Okay, and you know that this G naught guy, he's diagonal in K space, right? Because this is delta K, K prime, delta K, K prime. So basically, you know, you're going to have like G at some K, and this is going to give us a jump in Q, and then this is going to be at K plus Q, and then back again. Now, because this is a trace, this is off diagonal, right? Then it's going to connect between G electron and G hole. So basically what we get from this expression is just T over L cubed, that I also don't have too much time to explain, G electron of K, G hole of K plus Q, okay, times delta of Q squared. And then this delta of q, you can think about it as the Fourier transform of delta of x. So for example, if you expand this to second order in q, then it will give you the second derivative. If you expand it in first order in I omega, it will give you the first derivative in time, and so on. So what we get, so for example, S2 is equal to a sum over Q, 1 over V plus T over L cubed, sum over K, GE of K, G whole of K plus Q, delta of Q squared. Similarly, we can look at 1/4 trace of G naught delta, G naught delta, G naught delta, G naught delta. And this guy gives in the same way T over 2L cubed. So the point is, because the way we connect them one to the other, by the way, it might be helpful to have a diagrammatic, to connect this kind of trace to a diagram. It's helpful. So you can imagine that this connects basically to some field Q, which is the incoming, which would be like delta. And then there is some outgoing field, which is delta bar. So this is like delta, it's like delta bar Q. And then we have basically, you know, maybe this is K, and this is, this is like K plus Q, and this is K. So this would be like the holes, and this would be the particles. But we will see in a moment. Oh, maybe we should do it the other way around. Hold on. Sorry, this would be the electrons. Let's do it the other way around. Let's do it like this. No, I can't do it like that. So, okay, so sorry. So this needs to be delta bar, and then it's fine. So this is K plus Q. Okay, so what we're going...
so these are the terms of the Dyson series.
What?
These are the terms of the Dyson series.
No, I don't know if I would call it a Dyson series. It's just I'm connecting this trace to a diagram. Okay? So these two deltas here are basically, you see, this is like one field and this is the other field.
Right.
Okay? And then we have one arm which is K, and then the other arm coming back, which is K plus Q. But we will see that the holes that are K plus Q, we can actually invert them. Think about them as minus K minus of the electrons. Now this guy here, you can think about it, this guy here, you can actually think about it like this. So you can think about it like Q1, Q2, Q3, and then minus Q1, minus Q2, minus Q3 for conservation of momentum. And then each one of these guys, so let's say this is incoming, this is outgoing, this is outgoing, and this is incoming, just as an example, okay? Then we already saw that if it's incoming, you have outgoing electrons, like this, and incoming holes, like this. Then this guy, you know, already needs to have, if it has outgoing holes, because it's outgoing, like this guy, so it's outgoing holes, so it needs to have incoming fermions. And then this guy is exactly the opposite. It's going to be like that. So it's something like this. And then the momenta, we can just define it. It's going to be something like, you know, let's call this K. Then this is going to be K plus Q1. This is going to be K. Sorry, this is K minus K1, Q1. This is going to be K plus Q1 minus Q1 plus Q2, and then we have K plus Q1, minus Q1 plus Q2 minus Q3. Sorry, and this I need to indeed flip the sign because Q2 was incoming. Let me see. So, sorry, did I do this properly? So, outgoing I have Q1 and Q3, incoming I have Q2, and now I need to inject something that will cancel. So it should have Q1, Q3, but minus Q2. So it's actually the so it's this. Never mind, it's all balanced. So why does it help to do these diagrams? Because now you can balance everything, and you can just write this thing as a sum over some K. And then we're going to have G electron of K, G whole of K minus Q1, G electron of K minus Q1 plus Q2, and then G whole of K minus Q1 plus Q2 minus Q3. And this whole thing is then multiplied by delta bar of Q1, delta bar of Q3, delta of Q2, delta of Q1 minus Q2 plus Q3. And then it's balanced, this term. And this is a term, for example, that will appear in Ginzburg-Landau theory, and so on and so forth, and we can expand. Now, let's compute, for example, R. Let's compute R of t in this thing. Now I need to push ahead a little bit. How much time do I have left?
20 minutes.
How many?
20.
20 minutes. 23 minutes.
Yeah, 20.
23 minutes. So let's compute these terms. So for example, R of t, R in our Ginzburg-Landau expansion is 1 over V plus the Q equal to 0 of this guy. So it's Q equal to 0. So it's plus T over L cubed, sum over K, G electron of K, G whole of K. Okay? Now, that comes out to be equal to 1 over V T kf squared over 2 pi squared, sum over the Matsubara frequencies, an integral from minus kd to kd. That's our cutoff. Okay, so all our integrals are cut off because this is BCS theory, basically. Minus I omega plus VFK. This is GE. But the holes, remember that the holes are moving the other way around. Okay, the reason is because we permuted the particle in whole, but the omega did not. The omega does not change sign because we also did integration by parts, if you like. Or another way of thinking about it is that this k, this was like some epsilon of k. We also discussed it last time. So we get 1 over minus I omega minus b of k. Okay, so this would be g whole. Now this thing together, we can rewrite it. Wait a second. This is plus here. Plus. This whole thing we can write as 1 over v minus the density of states, integral from 0 to omega pi, the epsilon tangent hyperbolic of epsilon over 2t divided by epsilon, which is n of 0 t over tc minus 1. In a moment I should explain all this. So how did I arrive at this result? The first thing is I want to argue that t times omega times 1 over omega squared plus x squared, or let me write it like it's written here. It's minus I omega plus x, sorry, minus I omega plus x minus I omega minus x. This thing is equal to minus t over 2x, right? Sum over omega 1 over minus I omega plus x minus I omega minus x. Okay, so when I bring them together, the I omegas cancel and these ones add up. And then when I do the Matsubara sum, this will give me n Fermi Dirac of x, and this will give me n Fermi Dirac of minus x. And this just, if you calculate this, you'll find that this gives minus tangents hyperbolic of x over 2 divided by x, which is what we have written here. Good. Now that's one thing. Now the other issue is how did we arrive at this crazy result? So here we use the fact that this thing in the end gives us something like a log, right, of yeah. Okay. Maybe yeah. Another way of thinking about this is that if we take t to be equal to tc, you see that this whole thing is exactly the equation for tc, right? Because if I divide, like, imagine that I take this out. This is equal to n of 0, okay? 1 over lambda minus the integral from 0 to omega pi, the epsilon tangent hyperbolic of epsilon over 2t divided by epsilon, okay? So this guy is, when t is equal to tc, this thing is exactly 0. That's how we calculated tc. We equated this to 0. So, you can imagine that you expand this around t. So you can write this t here, you can write t as tc plus some delta t, which is t minus tc. Okay? And if you do that, and you have to trust me, then you get just 1. You basically just get 1. So it's trivial, and it comes out to be 1 t over tc.
So this is only up to first order?
T over tc minus 1. Yes, this is in first order in delta t. First order in delta t. Okay? So basically we obtained the first term in our Ginzburg-Landau theory. We obtained R. Now let's move to the next guy, which is the quartic term, U. Okay? Now the point with U, okay, is that here you can see we have here, this is not U. This depends on all these momenta. But if you remember, we had in our Ginzburg-Landau theory, we had this. Okay? So basically what we're going to do is we're going to neglect all the dependence on Q. It's similar to this. You see, for R, we neglected the dependence on Q. Here we're going to do the same thing. And then if I just take all of these electron hole, appropriately, you won't be surprised to discover that what I get is Tc over L cubed. Now I'm taking everything at Tc because you see this guy vanishes at Tc, which is exactly what we need, right? We need the mass term to change sign at Tc. So this guy is doing something special at Tc. It's going to 0, which exactly marks the situation where we go from this kind of potential to this kind of potential, right? This is R greater than 0, this is R smaller than 0. Okay? And that's happening at Tc. This guy is, we don't anticipate it to change sign, so we can just take it right at Tc. It's not doing anything special there. And then we have GE of k squared, G whole of k squared. And this then becomes Tc n of 0 Vf sum over omega integral from minus kd to kd dk divided by omega squared plus Vf k squared. By the way, notice that this Vf, this k in Vf is not the k we had before, it's k relative to the Fermi surface. Just to point out, so I made it shorter. Now this integral is something we can perform, okay, over k, okay, and then what we get is the sum over, so we're going to get pi Tc n of 0 divided by 2, 1 over 2 pi Tc cubed, sum over these omega n, 1 over n plus 1/2 cubed. Okay? Now here what I used is the fact that omega n, the Matsubara frequencies, are pi t times n plus 1/2. Okay, so after you do this integral here, this omega, you're going to get something that goes like omega cubed. Absolute value of omega cubed, this is this guy. And then I took out all the factors here. Now, this thing turns out to be, and this is easy to show, this is 14 zeta of 3. Do you believe me?
Of course.
But it's very easy to show it. Actually, this is kind of funny. Not that it's related in any way, but it's kind of the way you show it is okay. It's kind of nice to show it because
is it with the polylogarithm?
No, it's much easier than that. It's kind of straightforward. 1 over n plus 1/2 cubed. This guy is equal to a sum over n equal to 0 all the way up to infinity of 8 1 over 2n plus 1 cubed. So I just pulled out the 1/2, so I get this 8 here. And if you write this explicitly, you'll find that this is like 8 times 1 plus 1/3 plus 1 over, 1/3 to the third plus 1 over 5 to the third plus ta 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 ta. Okay? Which is exactly equal to 8 times 1 plus 1/2 cubed plus 1 over 3 cubed plus 1 over 4 cubed plus 1 over 5 cubed and so on and so forth, minus 8 times 1 over 2 cubed plus 1 over 4 cubed plus 1 over 6 cubed, ta 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 ta. Okay? Now this guy in here is just zeta of 3 by definition. Okay? And this guy, if I take the 8 out, then you just get zeta of 3. So altogether, this guy gives 7 zeta of 3. Oh, sorry, then this is 7 zeta. I guess. No, sorry. This is 14 zeta of 3. I'll tell you why. Because you have to remember that this sum, it's a Matsubara sum. It goes from minus infinity to plus infinity. So it gives you twice. So if you ask yourself where that zeta of 3 came from in all these expressions before, and remember, I want you to remember something when we do this. People measure, and I'll show you later, when we end, I'll show you a plot of an experiment where they see this jump in the specific heat with a zeta of 3. Okay? So this guy gives us, how much time do I have left?
8 minutes.
8 minutes. Oh, well, this is going to be stressful. So then this u comes out to be 7 n of 0 zeta of 3 divided by 8 pi squared tc squared. Okay, so what does this tell me? Then I can already do the specific heat. And this year probably I'll have to give up on the... Okay, we'll try to do also the coherence length. We'll do that in a second. But the point is that now, you know, if I think about free energy, where I have R delta squared plus u over 2 delta to the 4th, then I have that the average delta, the mean field value of delta, right, it's going to be the square root of minus r over u. Okay, or delta squared without the square root. And this is exactly the delta that we used in the previous lecture to take the derivative with temperature, right? But minus r over u, you see it's basically density of states, T over Tc minus 1, divided by that, 7 n of 0 zeta of 3 divided by 8 pi squared Tc squared. So this and this cancel, and we get overall, we get, minus. What?
I wanted to say about the minus.
8 pi squared, then we get TC, T minus TC, divided by 7 zeta of 3. And if you look backwards, I claim that this is minus d delta squared over dt at Tc was this part. 8 pi squared Tc divided by 7 zeta of 3. So you can look it up. So that gives us the specific heat jump. This closes. Now the last thing I want to do is I want to do the 1 over 2 eta. So we had in addition to that, we had 1 over 2 eta. This thing. And this thing comes from the expansion of this term to second order in Q. So we want to do d squared dq squared of t over L cubed, sum over k, ge of k, g whole of k plus q, at q equal to 0 is going to give us the second derivative. Okay, if we do a Fourier transform back, this is going to be q squared. It's going to be a q squared term. And we need a 1/2 here because it's a second, it's a expansion. And this gives us n of 0 vf squared divided by 3t sum over omega integral from minus omega d pi to omega d pi d epsilon minus I omega plus epsilon. This guy doesn't depend on q, so nothing is going to happen to it. This guy we take two derivatives, so we're going to get basically the same story as here, because we're going to get 3 factors of g whole. So we're going to get 1 over minus I omega minus epsilon cubed. And this 1 over 3 comes from these derivatives. Which gives us pi n of 0 vf squared divided by 12, 1 over 8 pi cubed t squared, sum over n, 1 over n plus 1/2 cubed. This guy is again 14 zeta of 3 divided by 7. And therefore we get that 1 over 2 eta is equal to 7 zeta of 3 vf squared n 0 divided by 48 pi squared tc squared. And then we can also estimate psi. So that's the superfluid, sorry, not the coherence length. So psi squared is 1 over 2 eta r. By definition, that's how we defined it. It's basically the ratio between this term and that term. This gives us, if you remember, it comes from this solution of the, this is how we define it. This is how we defined it. So this comes out to be 7 zeta of 3 vf squared divided by 48 pi squared tc squared, 1 over n of 0, 1 t over tc, which is equal to 7. Sorry, we need a minus sign here. 7 zeta of 3 VF squared 48 pi squared 1 over TC minus T, which comes out to be VF squared over 6 delta squared. So this gives you an expression for what is the prediction of BCS theory for the coherence length close to TC. Okay? And you see that it gives, indeed, this has units of 1 over length squared because this is energy and this is velocity. And maybe the last thing I'll say before I'll end is that we can also use we can also write something like 1 over 2 eta we want this to be equal to 1 over 2m grad psi squared. Okay? So we can use this where psi now has units of so this is mass, this is just mass. This has units of density and this has units of energy. So we can basically convert this thing and come to the conclusion that the ratio of psi bar divided by delta squared should be like 2m over eta, which comes out to be 7 zeta of 3 over 8 pi squared. And here we have n, like the rho naught, let's call it rho naught over Tc. No, this is the electronic density, n over Tc. This guy is just n of 0 times mu or something like that. We can, I can explain it, but basically it's straightforward. But the reason I'm writing it like this is because this is how it appears in Gorkov sub phys J E T P 36 1918 from 1959, equation 15. This paper, basically in this paper, he derives all of these relations, but this is maybe one of the most important ones, which is the relation between the gap that we write in BCS theory and the field psi that appears in the Ginzburg-Landau theory. Okay, where this m is like, the mass of 2 electrons or something like that. So this gives you kind of connection between the two. And here I think it's a good time to stop. So what I'm going to do is I'm going to give you 2 more exercises as one big exercise club. And if you hand in all exercises, then you will get credit for the course. Okay? Sure. For whoever is looking for credit. Okay, that's it.
יש לי שאלה
כן.
שלא יסתדר לי עם השאלה אני בהרצאות איך לחשב משהו ברחניישן.
כן.
אז נגיד אם אנחנו יש לנו את השאלה הזאת של ה-weekly interacting, אז יש לנו את האקשן, טסתי קצת, הגעתי ל-Z, להשגה הזאת. ואז כשרציתי לקחת את F, הגעתי לדבר לא יפה, לא הגעתי למה שאתה הגעת. בגלל שהבטא נמצא שם בפנים, אז באינטגרציה שמה זה שלוג של 1 חלקי בטא בחזקת בלבלבלה, ואז אני לא מצליח להגיע לביטוי כמו מה שאתה הגעת אליו בהרצאה שלך.
לא, הבטא הזה אמור להישאר פה לפי מה שאני זוכר. הבעיה שלך זה פקטורים של בטא?
כן.
זה הבעיה שלך? טוב, אני לא, עכשיו, הילדים שלי מחכים בבית, אני לא חושב שאני אצליח